Queensland, I think Queensland.
Queensland University.
Queensland University. So I'll hand you straight over to her now.
Okay, thanks for coming along to my session. I'm here today to talk about an open source tool called Apache Mahout and the opportunities it brings for web developers in terms of building the next generation of intelligent web applications. So I guess the first question you'd be really interested in knowing about is, what is Apache Mahout? So there's a few ways to describe it. I guess the most important being at the Linux Australia conference is that, yes, it is open source. Two, it's a machine learning library or a data mining library. It is in Java, which I'm guessing might not be the most popular thing at Linux conference. But nevertheless, don't let that scare you. It is designed to be scalable, so a lot of it actually will sit on top Hadoop. And if you don't know Hadoop, it's the open source Apache library that really facilitates the MapReduce distributed processing algorithm that Google published a paper on and has since become quite popular. So that's looking at it as a library, coming at it from the point of view that I want to actually use the algorithms that it has. However, it's also got a lot of plumbing in there if I was actually coming from it from another angle of I'm developing an algorithm, I'd like to parallelize it. It's got a whole lot of plumbing in there to help me do that a lot faster and deploy it through Hadoop, make it part of the library, and that sort of thing. So I guess the second question really is, what's in a name? And Mahout is actually Hindi for elephant driver, and if you look at the Hadoop logo, you see an elephant there. And so Mahout is, it makes sense that it's called elephant driver because it's really sitting on top that whole MapReduce infrastructure there. So again, it provides the plumbing for a framework. So things in machine learning that we use, like factor mathematics, matrices, collections to process things, the implementation of, or how it actually talks to Hadoop, it provides as a framework. There's also a lot of different types of algorithms that sit on top of it, and I'll come to that in a few slides' time. I guess if you look at it from this perspective of, you're just kind of moving into that space of, if you're building web applications, or any other application for that matter, where you might have, you're going to have to go down that path of making your application scale, and Hadoop becomes a nice option in that big data space. Then you've got this application layer that's sitting on top of it, where it's designed for a particular purpose, in this case either data mining or machine learning. And that kind of sits on the layer above that. And to me that seems like layers of abstraction. And if you come back to, we used to program a long time ago, it was assembler, and then you got C, and you got these layers of 4GL languages, and they made it easier all the time to actually get in and be more productive. So I see the same thing with building intelligent applications. You've now got the distributed processing, you've got your a set of algorithms up there, and you've got to ask yourself the question, what applications can I now start building on top of this? Given that it's going to become much easier. And I guess this brings a whole new question into play. If you think about what are the key skills that a programmer currently needs, a programmer or developer currently needs, and you think about, okay, you have to know a bit about databases, you're going to have to know about programming, maybe a web framework thrown in there, some networking, some security stuff. And as libraries like Mahout and others mature and make these new algorithms available, we can actually start building more intelligent applications. But also there's the process of, we're getting more and more data to process, and we need to have these applications scale. So I think it's becoming a necessity that we actually have some of these tools like Hadoop and Mahout in our tool set. And in some cases I feel this might be, yes, we're getting these libraries, it still might be a bit of a problem. So I think back, I've come in as a researcher into machine learning, again, after a few years. And I had this long break from when I did my undergrad, which was actually in engineering. And yes, they taught us probability, statistics, linear algebra. The problem was, some of it I didn't actually see the direct relevance of. And the second thing was that if you don't use it, you tend to forget it. And so I've come back in trying to relearn some of the stuff. But the other problem is a lot of our, classic IT degrees or computer science degrees, they're actually leaving out a lot of the math. And so my conjecture to all of this is you never know when you'll need probability and statistics. And so as I was starting to think about this presentation and what it was going to include, which was over the Christmas New Year break, this movie came on. And it had nothing to do with maths and, nothing mathematically or machine learning until there was this little segment that was played from it, which kind of had this really, I probably wouldn't use the word novel, but it was a very intriguing use of probability and statistics. So I'm going to show you a little movie. So who's seen the movie Equilibrium? Yep. Okay. That's good. So it will be new to a lot of you. Essentially, it stars Christian Bale. It's set in a futuristic world where, I guess, you're not allowed to feel, you're not allowed emotional content. And they've got a role which is kind of like a police or a detective that has learned a new style of fighting. And I guess I won't say too much more. I'll show you the video. There's a bit where it's going to start to get really violent, and I might stop it there, but
the gun carters. Through analysis of thousands of recorded gunfights, the cleric has determined that the geometric distribution of antagonists in any gun battle is a statistically predictable element.
The gun carter treats the gun as a toggle weapon, each move position representing a maximum kill zone, inflicting maximum damage on the maximum number of opponents, while keeping the defender clear of the statistically traditional trajectories of return fire.
By the rote mastery of this art, your firing efficiency will rise by no less than 120%. The difference of a 63% increase to lethal proficiency makes the master of the gun carters an adversary not to be taken lightly.
this is now the use of the math. I might stop it there. It's starting to get a little bit violent. And so that was just a little bit of fun I included there to basically let you know that you never know where you're going to need to use math, and it might come in handy for training as a grammatical cleric. Yes, it was all probability and statistics and geometric distributions that we used to work out the positioning that he needed to be in, not to get shot and take down a whole lot of people. Yes. And I guess the next key thing is you never know what you're going to discover. And so this was just something recently that came through, I think maybe a day or two. I found it on, just someone was retweeting it on Twitter. And it's actually done by a cartographer, and he was just looking for geotagged tweets for all states in America and looking for profanity. And so you basically, because if he's used contours, it's basically you've got mountains of profanity coming from different places. And you might not be able to see very clearly, but Utah is actually not included in any of that. And so you kind of beg, does anybody use profanity in Utah? So I'll move on now to the algorithms that I included with Apache Mahout, and they fall into 4 different categories. So there's recommendation, which we all encounter when we surf the web or when we're buying something. There's also clustering classification, and more recently we're starting to see the inclusion of evolutionary algorithms, things like the traveling salesman algorithm and some genetic-based ones. So I guess I've included the slide just to kind of illustrate that the algorithms that are being implemented are actually the ones that are the most used, and they've been the most influential in terms of getting used academically as well. So there was a paper that was published in 2008, and it basically looked at what were the top 10 data mining algorithms, and a lot of those are actually included in Apache Mahout, and there's some that are actually being worked on at the moment for future releases. Now I'm basically just going to look at just getting you up and running to actually try some of this yourself. Java 1.6. If you're going to plan on building from source yourself, you're going to need Maven, which is a build tool and a dependency tool for Java. And you're also going to have to download Hadoop. So I guess even if you're not setting up a mass cluster to actually process stuff, and you just had a single computer, you can still set up Hadoop to run as a single computer. And a lot of the algorithms that are included there, just when you're starting off, quite an easy entry into it, they'll actually run in memory. So you don't have to go through that whole setup first or beforehand, which I don't necessarily want to trivialize the setup of Hadoop in that underlying layer, because Hadoop obviously does a lot of complex things for you. And if you were spawning out to hundreds of machines, you're going to need to know a lot there. If you're just coming at it from the machine learning angle and you're starting small and then going out, I think you can actually start from Mahout, just set up a few things, and you'd be right to go. So if you've downloaded the distribution, it's really just typing, it's got all these command line launches, and if you just typed bin/Mahout, it actually will list all those little command line launches that are included in there. And I haven't included all here, but you can start to see a lot of the algorithms and some tools to actually help you format data into the right formats. And then choosing an algorithm to run, it's really just bin/Mahout, a space, and so k-means, which is a very simple and popular clustering algorithm. You can go --help, and then basically you'll get the options that you need to pass to it as well inside there. So I guess there's something coming up from here, is that even though it is Java, a lot of the way you're going to use the library might be command line based. But I might stress, even though I haven't included it in any slides, you can actually still do Java-based programming for additional processing that then calls this. And it does include Maven POM files to help you basically in a tool like Eclipse, which is an IDE for Java. So scaling out, obviously, you're going to need those conf files for Hadoop. And when you're starting to scale out, you really need to use the driver classes to run your jobs. So I'm going to move now on to all the different classes of algorithms that it encompasses. And the first is really clustering. And clustering is an unsupervised machine learning technique. It means, and that essentially means that the algorithm can actually find patterns, and you give it a similarity measure, and it can find groups based on that similarity measure. Where does the word unsupervised really come from, and what does it mean in that context? Essentially, it means that the algorithm, given a particular metric, will discover things inside and show them to you. When you look at, from the other hand, supervised means you might manually have to classify things yourself, learn the features of that, and then use that to train a model, which you can then reuse. And so there's that human element in there where someone's physically had to train something. So that's what we call supervised learning. Unsupervised, it can learn it on its own. So clustering is really quite good for finding patterns and exploring data. it's something I think Mahout at the moment excels at because it's got a lot of algorithms, you know, k-means, mean shift canopy, Dirichlet model processes. And there's even this newer algorithm, and I'll talk about this a little bit later, which I think is quite powerful, called Latent Dirichlet Allocation. And again, because clustering, to find patterns, it uses like distance measures. So it's got a whole lot of different classes of those that you can use. So going into this, this is just a little bit of background if you're wondering. We talk a lot about, and even in starting to use Mahout yourself, we talk a lot about vectors, and we can, you know, have that represented as, you know, an x and y coordinate. You can express it as an array or as a hash map. When we're processing documents, we tend to make these matrices, and it's basically, we'll take every word that we find in the document, and we start a count, which is, you know, it's a frequency count, so how often is this word used? And we're kind of creating this matrix that's got, you know, documents with words that are used. And then that, again, has a resulting vector for a particular row through that. There's actually a bit in Mahout that's included to help you do some of the hard work sometimes. So, you know, multiple words sometimes need to be grouped together. So, you know, if we had Linux conference appearing a lot, you'd want that to be, you know, included together as a phrase and not just separate words. Mahout's got some tools for, you know, normalizing that matrix, applying weightings based on how frequently it's used. And I guess also you don't want words like is and a and the appearing, so, and that's what we call stop word removal. So there's tools inside Mahout. I haven't directly listed them there, that will actually help you do some of that stuff. A lot of these sort of, you know, text analysis ones are actually coming from another project, which is for a search engine called Lucene. And it's actually where Mahout actually began, in one of the subdirectories there. So when they moved it over, some of the stuff came with it. This is just a little example of, you know, going from a directory of text files and applying a k-means algorithm to cluster it. So there's a command line tool called seek directory, and that basically, you can give it a path to a folder that contains a whole lot of files. It will output a sparse vector, and then you use, so basically that's going to output the sequence file. Then basically you use seek to parse to actually put out a sparse vector, which is really just a nicer and more compact way of expressing that vector, where if a particular word is 0, it's not actually included to make it really long. And then you can basically just run k-means by, you know, specifying the vector input, where the output is. And then there's this other thing here called k. And that's quite important, because a lot of these algorithms work, they don't, you know, at the moment you can't basically say, discover all the groups for me. You basically, the way k-means work, and the fact that it's actually called k-means, is that you specify the number of groups that you want to find, and then it tries to fit things to those groups. And that's quite important, and so k is specified in there. And there's some helper tools also, so basically outputting the results of the clustering. And that would seem quite easy enough, right? You know, I've installed Mahout. It's got these command line tools. I've got some data. I can go off and do stuff. And so, yes, let's all go straight ahead and build all these intelligent web applications. And, you know, I say, yes, that's easy enough, and I've put a but, and it's actually quite a big but. You can't just run these algorithms and just expect them to give you good output. There's a lot of experimentation involved. There's data exploration involved. You know, so finding the right k for your purposes, what similarity distance metric is the best for my data. And that's, I guess, you know, software tools become available, and then when we start applying them, there's these new skill sets that usually come about. And so, you know, it's really kind of pushing forward this idea of the data scientist. And, you know, you're going to have to explore your models. You then have to test and evaluate before you can roll them out. So the point I'm really trying to push here is that it's quite easy to get into, once you do get into it, you get other levels of complexity, which more lie in that sort of, is this algorithm correct for me? What are the correct parameters that I should be passing? How am I going to test this? The next set of algorithms that Mahout has are recommender engines. And I guess these have to do with marketing products to us, so obviously we see them the most on the web. Anything from, you might be interested in these books or these movies. They essentially try to infer our tastes and preferences and try to specify new items to us. So Mahout, when it started up, actually incorporated another library called Taste. And then there's still some of the Taste algorithms in there, but I think also new MapReduce-based algorithms were introduced. So it can do both user and item recommendation, and it's also got a framework for basically, so obviously once you build your recommendation, your model from that, you can then store it either online or offline, and then you can also then use it to make predictions in real time. It also includes a number of similarity measures, and the most commonly used ones I've listed over there. Not quite sure where this algorithm actually fits in terms of the main classifications, but it's something called frequent pattern mining. And from sequences it can find patterns inside a sequence, and so you could either look at sales transactions, if what people bought together. So it might bread, milk, eggs, and it might sometimes throw up some things that you wouldn't quite have predicted, but when you actually see them, they turn out to be quite true. So a lot of papers I've seen where they've done this sort of analysis, it turns out that whenever somebody rushed off to the store and they bought just nappies, they also ended up picking up something like cigarettes or beer. The original algorithm for this was a priori, and to actually find the sequences, it would have to do a whole lot of candidate generation. So the algorithm was quite intensive in that it would have to try and predict every sequence and actually write that to disk. Then about a couple of years later, a new algorithm, FP growth, came out, and that didn't require full candidate generation, and so it was much faster, and so Mahout has this parallel implementation of it. The next type of algorithms you find are classification, and ideally this is where you have a pretty fine set of classes, or you can call them categories, and you get some new input, and then basically you want to decide whether it matches a particular category, so you can put it inside there. And this is where I come back to, it's a supervised machine learning technique, in that you're going to have to pre-train a model to what each of those classes are, and then you use the features to actually then decide what it is. So it's not going to naturally be able to put it there. There's some training, a development of a model, and then some evaluation that will go into it before you can actually deploy this. So there's a heap of algorithms. I guess in the last 10 years, the most popular classification algorithm is actually a support vector machine, which I've put down as SVM. And in I think the latest release, which is 0.4 of Mahout, that's starting to appear on the trunk. So that's obviously quite exciting. So again, as I said, basically you learn a model from a manually trained data set, and then you predict so an unseen item or an unseen object, you basically can predict where this would, under which class or category this would fall into. So I've covered off all the different main classes of algorithms that are currently in Apache Mahout. I'm now going to move on to essentially a new algorithm. It falls under clustering. Particularly came out in, I think, 2003. It's called Latent Dirichlet Allocation. And the main use for this has really been topic modeling. And topic modeling is really just, if you're going to do clustering, but you're going to do it on text. A lot of papers and stuff have actually been calling it topic modeling. And latent Dirichlet allocation, or LDA, seems to be the main algorithm that's being used for that. What's really interesting about this algorithm is it's not a hard clustering algorithm. So it's not trying to, make separate little clusters. What it can do really nicely is to say we can allow for overlap between what the different classes are or what the different groups are. So as you can imagine, that becomes quite a useful thing for text, because sometimes you might have a document and it might discuss one or more topics. If you just took that and wanted to classify it, the predominant topic's going to get, it's going to base it on the predominant topic. And that's not to say that the rest of the document is not important as well. So you want a way to actually relax that restriction and be able to say this particular document might belong to this topic and that topic and that topic. So I guess you start off with that term document matrix that I talked about previously. And LDA will actually produce a word to topic mapping and also a topic to document mapping. And you can then basically infer what that multiple overlap was by reading from that matrix, reading from the two matrices. In terms of actually determining how many topics the algorithm finds, it's something you actually have to specify. Yep. No. So, I mean, to find k, you can do it. There's a number of ways. Like I've seen mathematical papers on how to determine the ideal k. In my own research, I think what I'm trying to do at the moment is when you actually put this in front of a human, how do they determine k as well? And so I guess I read a really interesting paper. I think it's from the NIPS 2009 conference, and they were looking at. It was actually very interesting because the workshop at NIPS was called Clustering Science or Art, and there was a paper inside there where they started looking at all the metrics that we use to evaluate clusters in terms of purity and accuracy and stuff like that. And they were actually saying that we do it quite mathematically, but we don't actually take the algorithms out to users to test them very often. And that was the first interesting paper from that session. And there was another one that came around, and it was, humans are quite good visually at being able to determine, clusterings, how to group things. And it was actually looking at algorithms that can try and match that performance in terms of vision. And there were a few they mentioned, like eigenmap and pggap, where you can actually try and find what that ideal density is and to determine that k. Yeah. But at the moment, what I've been doing in my own research is to try and look at how users react to it. And there are studies that do show that, even if you take a small amount of documents, something like 20, and you gave it to a whole lot of different people to actually organize into groups, they all come up with different things. And so I think there's some experimentation and interaction that needs to happen when you actually put this in front of users. So the example that I've given here is really if you had, your documents can be tweets. We'll go with the whole of Twitter, because I think lots of people are doing a lot of text analysis on tweets and hashtags at the moment. Essentially, each tweet maps to a document, and then you can include each of the words included in there and do a word count. You pass this to the Latent Dirichlet allocation algorithm. You specify how many topics you think it should be putting them into, and you get these two. It's really looking at probabilities and multinomials, but I've tried to simplify this as much as possible. You can basically get back these two matrices where you can map topics to words, and you can map documents or tweets in this case to actual topics. And so what you can do basically is you can display that quite interestingly. So you might go, this is topic 1. These are the main predominant words that appeared in topic 1, and we can also then do a listing or link to each tweet. These are the most prominent tweets that belong to this topic as well, and that greatly helps people actually interpret what that topic or theme might be about. So I've just included, some code here. It's actually not. I wouldn't actually call this code. It's actually command prompt driven, running the LDA algorithm after you've done some pre-processing to get your data in the right format. Input, output, and it's got an topics thing. And there's also a helper method to display the topics called LDA print topics, which will give you, something similar to what I was describing previously about being able to list the main words and the main documents that were for that topic. There's some new work starting to emerge on how to visualize this, because this technique is quite useful for visualizing really large document collections. So I've seen a few papers on basically taking that output and doing a visualization on it. And I guess that's an interesting space as well. So I've got this idea to actually build a little application that can suggest members for Twitter lists. So the feature of a Twitter list came about, I think, sometime last year. And prior to it, you just really had your timeline, and you could use a whole lot of other tools that maybe you could group users into. And so the feature list really allowed you to put specific people into a group, call it a list, and then when you basically went to that list, you'd only see the timeline of tweets from those users. So it was a nice way of breaking up things, particularly if you were following a lot of people, or a lot of people followed you, or you just wanted to create lists that you want to share with others about specific topics. And so the idea was to actually build an application that could actually recommend lists, which I would interpret as more of a clustering problem. And I think the algorithm that I would use is LDA. And one of the things using LDA will bring with it is that it will allow for overlap. So, people obviously talk about multiple topics, so it wouldn't be that one person only belonged to one list. Like, it could actually, what the person was talking about, he could belong to those particular lists. And I guess, just those little things you have to do. How do I interact with the Twitter API? So, having a look at that, I can get a list of the followers. I can retrieve tweets for each person. And then, when I got those groupings, I can actually save them back to Twitter. In terms of data processing, obviously we're going to need to combine all the tweets for a particular person. Just things like removal of stop words, stem the words, and then basically create our user word matrix. And that can then be packaged into a UI, which behind the scenes will obviously be able to authenticate with Twitter. It can display suggested lists, so that's what I was talking about before, getting a best estimate for K. And it would also allow users to interactively change the value of K and then see the list that would emerge from that, and then basically try to let them reorganize it via a GUI. And I tend to really like jQuery. I think of myself as a machine learning and jQuery person, which I think is a little bit of an odd mix, but I've actually built interfaces for these algorithms, and I've been using a lot of jQuery. So we'll use jQuery sortables, which will allow you to actually manipulate between lists, and then you can save them back. So that was just a little idea, basically, that I had for trying to use one of those algorithms in a practical application. So I guess, in terms of looking for resources to help you, and I use the word gently, get into machine learning and get that sort of get an understanding of the algorithms. The book that I would almost go as far as saying changed my life is called Programming Collective Intelligence. It's by Toby Segaram, and it came out in, I would say, maybe late 2007. And I think what this book did was it used a whole lot of algorithms, but it used them in sort of a Web 2.0 manner. So all the applications were really practical, but it also had really, really good explanations of everything, where it was more the concept of the algorithm that was pushed forward. And then it went on and actually practically implemented everything in Python code. So it was a very accessible book. So coming at it from someone that's been, working in web development for a few years, it actually exposed me to a lot of things that I hadn't heard of before. And it did so in a very, very nice way, and it was a very, very easy read. And so for anybody interested in learning more and doing it practically, I would recommend that book. The second book is a book called Mahout in Action, and it's got the little sticker of MEEP, which stands for Manning Early Access Program, which means it's been actively being written, but the publisher's making chapters available. And I basically ordered it when it had like one chapter, and I've been, holding out for the emails that come with where's the next chapter. So I'd have to recommend that book. And I think they're just up to almost having all the chapters in there. But it covers basically everything from installation to how all the algorithms actually work, and then basically into how to put them into practice yourself. The only sort of thing with that one is it's got a lot, it's not tending to really use Mahout from command line all that much. It does a lot of coding, but I think when you get into more complex applications, you're going to want to script a lot of stuff yourself. And so there's a little bit of Java to learn there. So I guess to summarize everything that I've been through today, I think Mahout is a really good library. It offers good abstraction over, when you think about, when I started this presentation, I was saying, there was distributed processing, and Google had this idea of MapReduce. Hadoop basically picked up those ideas and made it, put it into a library that then became reusable. Not to trivialize what Hadoop's actually doing, because there's a lot of hard work in terms of distributing the data, collecting the data back, as well as just managing all the actual servers in the cluster. And so on top of that level, you've got these algorithms that have come about. And so it's another layer of abstraction. And I guess on the one hand, that makes it really easy for us to come in and say, I want to use these algorithms and I want to build stuff onto it. And that's what's good about it. But I mean, historically, whenever this type of thing has happened, whether it be assembler and now we have C, or C and now we have a 4GL language, there's always going to be a bit of a learning curve, and new roles get discovered from that. And so if we're naive enough to think that we're just going to run these algorithms and they're going to work miracles for us, that's obviously not going to be the case. There's a lot of data analysis and data exploration and building of models, and basically even just getting to know which algorithm is good for what, which introduces this whole new role of a data scientist into the scheme of things. And I guess that's where we're really heading, and that's what the future is going to be, where it's not just going to be the big players like Google and Yahoo being able to do intelligent web stuff. It's going to be everyday web developers that are going to be able to include these capabilities in their applications. And also, one of the nice things that comes from all of this is, with a lot more people doing it, I'm sure there's going to be a lot more ideas coming from it to create that next generation of application. And as a side note, I give the LDA algorithm, which came out in 2003. By around about 2007, 2008, there were papers published on how to parallelize it. And the next thing you know, it's now in a reusable library. So even as a research platform for actually prototyping new algorithms that we then want to be able to distribute, I think there's a little research niche that Mahout actually fits as well inside there. So just to end on a bit of a fun note, I thought I'd list 3 algorithms, and they don't necessarily fall into any of the types of algorithms that I've actually showed you, but they do kind of useful things. So they're fascinating to me. When I saw them, I kind of wondered how were they actually done, and what's the maths involved with them. One, I might warn you, I also found a little bit disturbing. But so the first one, and I listed as my number 3, was an algorithm that could identify how, basically identify whether any image was manipulated with software such as Photoshop or GIMP. And it's, Photoshop's often used to touch up images, and it'd be good to know, whether it was touched up or not. And the way they built this algorithm was that just looking at lighting and being able to, say that the lighting across the whole image was the same. And using that, they could then actually discover what was pulled in from other areas or changed. I've included a link for a write-up on more of that. So the second one, or number 2 on my list, came out a few years ago, and I think in the current version of Photoshop, was just released late last year, it's actually included because the guy that was working on it actually got employed by Adobe. And it's called seam carving. And essentially you could, it looked at the energy levels inside the image, and you could resize it, but it would try and take away bits that were unimportant. And so I've basically got the image over here was much broader, and seam carved, it actually, you can see, it's actually compressed some of the things, but not in the way that you'd normally scale an image. If you find that a little bit intriguing as to how that works, there's a few YouTube videos from the author himself and giving examples about how it works. And I just listed it here as one of those fascinating things. And immediately after it got released, there were a whole lot of people that made libraries for Flash and libraries for all these things to actually start doing that and playing with it. And I've changed the heading here to, instead of fascinating, to disturbing. But there are researchers that actually use a technique called support vector regression, and they use it to improve features in face images. And so I think this would start off as a whole library of what someone would term beautiful people, and they work out maybe commonalities of, try to work out the features about why they're, or why they're beautiful people, and then they can apply changes to any images. And I find this a little bit disturbing for the obvious reasons, but then it kind of intrigues me for other reasons. It's like, well, how do they actually change the facial features without completely destroying the image? And that's still a little bit fascinating to me as to how that's actually done. But so they have a, they've published, and they usually put up pictures inside their papers. But I also found they did it to Madonna as well. And then they went as far as trying to do it on Shrek. So I can't really tell how far it's worked on that one, but so there you go. And that was just something a little bit fun to end off with. But I guess discussion or questions, and I always start with a question for me, but I guess I have a question for you to think about, which is, what will you build?
My question is on the user and item recommendation engines. What sort of metrics, if any, are needed to implement that, and what size data sets does that work well on? Okay, so I mean, I'll answer the second part of the question first. With all machine learning, the bigger data set you have, with the more features you can capture, the better. If you just wanted to experiment, like if you didn't have your own data set, there's the Netflix one that's using a lot of competitions, and Group Lens is another one. And there's tutorials for running that on the Mahout tutorial website. The first part of that question, you're really looking at things like cosine distances, Euclidean distances, and they're all included in there. And when you actually build your recommendation system, you're going to need to experiment with those a bit to see what's actually matching your data to give you those good results. I guess the important thing to kind of remember with all of this is, and a good example for, give you a feel for these things is, when they were having the Netflix competition and you had all those groups of teams competing to try and get the best prediction, people used standard algorithms, but then it was a whole lot of tweaking with other algorithms by trying to understand the data that actually got them the good results.
So there's always that room for experimentation. And so I would, if I was doing it, I'd go through all those distant metrics and see what was working for me before I built, while I was building that model. Okay. Yep.
Do you know of any projects that are using Mahout yet? Doing anything interesting?
So, there probably are quite a few. I just don't know any offhand. Yeah, I can't really think of any offhand. So, to me, it's been quite useful in my own little projects, and just having that standard framework there and having all those algorithms, But I guess the other thing is it's version 0.4 at the moment. So while there's a good community and a lot of people contributing to it and testing it, and I can't say that I've had any staggering bugs with it, but I can't really give you firm names as to who's been using it.
Right, one more. There we go.
Just on the what will you build with it, I work for a Brisbane text analytics company, and we have a lot of the clustering, classification, stop word removal in our software. Where we don't use Apache Mahout, but I think we'll probably look at it now. We have a couple of products that we're thinking of building or have started building based on that sort of technology. The first is value-added search. We prefetch the first 30 or X number of search results when you do a search, and there's some search APIs provided by the big search people that allow you to directly plug into their search engine, execute a search and get the results back. We prefetch those first 30 or so and then use the clustering, classification, stop word removal, etc. to get a summary of those results and then present a Wordle-like image to you to show you how they work, and then based on those results you can get back to direct web pages that, let's say if you search for iPhone review, you could see specifically which web pages are talking about screens in their reviews and stuff like that. So it sort of allows you to magnify your search after the fact. Another product is Wordle, but with meaning, where the words are placed. So instead of just putting the words in random spots and adjusting the size based on repetition in the text, we do that as well. And that's about it.
Okay, that's very interesting that you're starting to use Wordle for visualization. Have you heard of something called tag clouds?
So what we do in our software is concept maps at the end.
Right.
So
Okay.
what we're doing is we're taking the word and adding context to the word.
Right.
Graphic where the words appear in the tag cloud, conveys the meaning and how they relate to other words.
Okay. Sounds very useful. Yeah.
Thank you very much. We've now got to take a break for lunch. And but before we do that, I'd like you all to put your hands together for Aneesha for an excellent slide presentation. And Aneesha, I'd like you to accept this on behalf of the LCA.
Thank you.
It's a macadamia nut bowl. Thank you very much, everyone.